Can you look at the simulation and say, oh yeah, that's right? Or do you need to then actually do the experiment in a lab to confirm that it's right?
So this is a very interesting question. I think we are still at the stage where you will need to do some experimental work, but the idea of the technology that we have at this stage is that is minimizing the amount of experimental work that you will need to do. In the future, as the technology evolves, we will reach points where I have no doubt that quantum mechanical calculations will be more accurate than experiments. And then it will be actually a very good question whether the people who do the experiments will have to run the calculations to check that how good their experiments are.
Right, because Luan was explaining there can be other factors like the room temperature, the air pressure, and all that.
There are certainly external factors, right? And so that is something to take into account. But it is all included in the laws of physics that we know and can apply, right? So it's more of a computational problem. If we were able to have more computational power in the future, we'll be able to model also the environment around these things and account for the effect of temperatures, humidity, and so on. Of course, this is a very early stage, and this might happen, I don't know, in 15 or 20 years. But we shouldn't underestimate the fact that so far computational power has been increasing exponentially every couple of years.
Yeah, and did you run this on computers even faster than Gaudi?
Oh yeah, absolutely, yes.
Yeah.
So this the world records were broken on the largest machine on the planet, which at that time was the Summit supercomputer at the Oak Ridge National Lab. But today we are also using the #1 machine, which is the Frontier machine still in Tennessee at the Oak Ridge National Lab, which is the first exascale computer. That's the other very attractive feature, right? So you're just using the fundamental laws of physics, so there is no limitation in terms of what you can model and simulate, whether it is modeling and creating new catalysts for, better, more efficient production of second generation biofuels, or hydrogen storage, or carbon capture. It doesn't really matter, right? The fundamental laws are the same. There may be an increase in the complexity of some aspects, but the underlying laws of physics are those of quantum mechanics, which is the Schrödinger equation, which is ultimately what we solve when we run these calculations. One of the main issues associated with the current way of designing drugs is that it's all based on heuristics, which were gathered through the past, right? So, and this is still, to a certain extent, not completely, but mostly true. If you look in general at how chemical synthesis is done and the compounds that are explored, the reactions that are explored, there's history there of successes, and you build on top of that. But that, it's all heuristics. Instead, we have the freedom of exploring anything, if you want, in terms of what are the potential chemicals and potential chemical processes that can happen, because our oracle, so to say, it's not the past, it's just the ground truth of the physics.